Have you ever just looked up at the sky and wondered, why? Why is it that specific shade of blue? It's a question that sounds so simple, right? But the answer is this incredible scientific story that we're going to unpack today. We're diving into atmospheric scattering to uncover the secret behind our blue sky. So yeah, let's just get right to it. It's the classic question, the one you ask as a kid. And you'd think there's an easy one-sentence answer. But the truth is, it's this beautiful, complicated dance between sunlight and our atmosphere happening miles and miles above our heads. And that dance, well, it has a name, atmospheric scattering. And what's so cool is that this one idea doesn't just explain the blue sky, it also explains the fiery reds of a sunset, the brilliant white of a fluffy cloud, and even that hazy gray look you get on a polluted day. It's all connected. So what exactly is it? Well, put simply, as sunlight travels through our atmosphere, it's not an empty highway. It smacks into tons of tiny particles, gas molecules, dust, water vapor, you name it. And when it hits them, the light gets bounced around in all directions. It's kind of like a giant cosmic pinball machine for light. But here's the secret, the key to the whole thing. Not all of that scattering is the same. It all comes down to one crucial relationship, the size of the particle that the light hits versus the wavelength or color of the light itself. That single matchup changes everything. So in this game, we've got three main players, Rayleigh, me, and non-selective scattering. And really, the only thing that separates them is the size of the particles they interact with. We're talking everything from unbelievably tiny gas molecules all the way up to huge water droplets. Let's get to know them one by one.
All right, time to meet the scatters. We're going to take a closer look at how each of these three types literally paints the world that we see every single day.
And we have to start with the star of the show, the most famous one of the bunch. This is the one that gives us that brilliant blue sky, Rayleigh scattering. So Rayleigh scattering happens when sunlight hits particles that are incredibly small, way smaller than the light's own wavelength. We're talking about individual molecules of nitrogen and oxygen, the main stuff our atmosphere is made of. And because these particles are so tiny, this type of scattering is super picky about the color of light it interacts with. And the physics here is just wow. There's a rule that says the shorter the light's wavelength, the more it gets scattered. But get this, it's not just a little more, it's exponentially more. That little formula there basically means that short wavelengths, like blue and violet, get scattered way more powerfully than long wavelengths, like red and orange. And boom, that's the answer to our original question. During the day, that powerful scattering sends blue light careening all over the atmosphere, so no matter where you look, you see blue light coming at you. But at sunset, the sun's light has to travel through way more atmosphere to reach your eyes. By the time it gets to you, almost all the blue light has been scattered away, leaving just those longer, less scattered reds and oranges to create that amazing spectacle. Okay, on to our next type. Let's talk about me scattering. This one happens a lot closer to the ground, where things get a bit messier. Me scattering is caused by bigger stuff. Things like dust, pollen, smoke, pollutants, all the things hanging out in the lower atmosphere. Now at this type, the particles are roughly the same size as the light's wavelength. And because of that, me scattering is not nearly as selective about color. It scatters all the colors much more evenly than Rayleigh does. And what's the result? Well, the next time you see a hazy day or a gray plume of smoke, that's what you're looking at. That's me scattering in action. It's grabbing all the colors of sunlight and mixing them all up, which to our eyes just looks like a washed-out whitish gray light. Which brings us to our third and final type, and honestly, it's the most straightforward one of all, non-selective scattering. This happens when the particles are much larger than the light's wavelength. Just think about the water droplets in clouds or fog. I mean, they're huge compared to a wavelength of light. They're so big, in fact, that they don't care about color at all. They're completely non-selective. They just take all the visible colors, red, green, blue, the whole spectrum, and scatter them all equally. So, what happens when you take all the colors of the rainbow, scatter them equally, and mix them all back together? You get white light. It's that simple. And that is exactly why clouds and fog look bright white. So, okay, we get it. Scattering explains the world we see from the ground. But this science isn't just for appreciating a pretty sunset. It becomes absolutely crucial when we want to look at our planet from a completely different viewpoint, say from space. So let's think about this for a sec. If the atmosphere scatters sunlight on its way down to the ground, you know it has to be scattering the light that reflects off the Earth on its way back up to a satellite, right? So how does all this interference mess with what our satellites are actually trying to see? Well, for starters, Rayleigh scattering adds that blue haze to satellite images, which can wash out details and make it hard to see things clearly. Then you've got Mie scattering from dust and pollution, which can flat out block the view of the ground, making it tough to monitor cities or track things like wildfires. Scientists literally have to build complex computer programs just to try and undo these effects. But non-selective scattering, that's the real showstopper. Because clouds scatter all light so effectively, they're basically like a giant white wall. If a satellite is trying to take a picture of the ground and there's a cloud in the way, game over. It's the ultimate roadblock for this kind of technology.
Okay, let's bring this all back home and do a final, quick recap of our 3 atmospheric artists.
So let's review. You've got Rayleigh scattering from the tiniest particles, giving us our blue skies and red sunsets. Then there's Mie scattering from medium particles like dust, creating that whitish haze. And finally, non-selective scattering from the biggest particles like water droplets, giving us our bright white clouds. 3 totally different processes, all working together to create the atmosphere we live in.
And that kind of leaves us with one last thought to chew on. The light that gets to us, whether we're on the ground looking up or in orbit looking down, is never really pure. It's always been filtered, bounced around, and changed by our atmosphere. And it makes you wonder, if our view is always shaped by this beautiful, chaotic dance, what other subtle details about our own planet might we be missing?